Okay, so the reason to give this talk is, number one, I don't know anything about deep learning. So I do know a little bit about SQL, and I do know that SQL, if you really think about it, it's probably like the original big data technology. SQL is a very old technology. It came out in 1974. So we're talking about something that came out in 1974 with historical standardization in 1986, ANSI standardization, and then standardization, further standardizations in 92, 99, 2003, 2006, 2008, 2011, and 2016. So it's a very old technology that is absolutely ubiquitous that people are still adding onto. Unfortunately, I think this is one of those like you learn in school type technologies. You know, if you talk to anybody who learned computer programming in grad school, there's this list of technologies that they learned once 10 years ago, and they never really bothered to refresh on, like make, or shell, or SQL, or even things like matplotlib. Some of you here are still writing matplotlib like it's 2003. But it's a tool that's under active development, and there are new and proper ways to do things that might have been difficult a long time ago. I think this is actually why it's relevant to talk about SQL even in 2018, because even for such an old technology, it still is a very actively developed technology and a very powerful and robust and mature technology. So I'll give you the broad agenda of where we're going. Now, the goal of this talk is to talk about data modeling and relational data modeling. I think that data modeling is one of the most interesting things that we can do as computer programmers. It is the hardest part of our work to actually automate because it requires really fundamentally understanding a business domain and reducing the complexity, the infinite profundity of the real world to something that a machine can automate. It requires a lot of insight and a lot of thought and a lot of vision in terms of what the tool that you're building actually does. I want to talk about the data modeling, or maybe the SQL approach, and some interesting features you might not know that are actually in SQL. A couple of things which you might have thought are very difficult turn out to be fairly easy. So things like managing tree structures, simple features like common table expressions, the idea of temporal modeling, and how powerful an idea this is, and some additional mechanics like window functions and some SQL DDL mechanics. So when I started writing the notes for this talk at 4 a.m. last night, this seemed like a really funny joke. So the agenda is this. The agenda, get it? Like there's an agenda and a the agenda? Yeah, it really seemed really funny at 4 a.m. What we're going to do is we're going to create some rules for a simple game. We're going to define some queries for that game, and we're going to try and model certain aspects of that game. We'll use a game rather than the typical example of payroll or some business problem. It's a little bit more interesting, and it allows us to do things that are a little bit more complicated without seeming too synthetic. Now, I want to tell you what the no-genda is. That's what we won't talk about here. This really seemed like a funny joke last night. The no-genda is to talk about things which I don't think are actually that interesting, such as the boring details of the SQL standards. They are excruciatingly boring documents, and there are many, many of them. Things like performance. One of the reasons why I think people still like SQL is not that it's necessarily a more performant technology, so much that the performance of SQL is well understood. If you have an SQL database or some queries, and they're slow, the mechanics of how to make that fast are well understood. It really is, from the perspective of a business, let's just throw money at it, because there are plenty of people who have expertise in tuning Oracle or Postgres or one of these other tools, and the actual details of how to do that has been covered to death. So we won't talk too much about performance. What we'll do is we'll talk more about modeling and what you're capable of doing. So that's the general idea of where we're going to go in this talk. I will live code this entire talk. So what we'll do is, just to set the baseline in the agenda, we'll focus on Postgres, because it's probably one of the best open source SQL databases that we have access to. It has a lot of really interesting features. It's open source, it's free to use, it is a fantastic, mature, sophisticated tool. We will use certain features that are specific to Postgres, so we'll ignore things that are maybe in the standard but not generalized throughout all the different products. And it allows us to be a little bit more specific in this talk. So as I said, the example that I want to do, and I want to motivate some of these things with a very concrete example. The example I want to give you is of a game. Because this is one of the most interesting data modeling exercises I've had to do recently. I was thinking of creating a collaborative coding game, a game for teaching coding. I think I briefly talked about this last year in a lightning talk at PyData Berlin. I haven't been working that actively on it. It's taken me a year to do very little work. But as you can see, even a fairly simple set of rules leads to an interesting opportunity to look into how the database allows us to model information, to enforce constraints, and how it drives us to really firmly understand the technology. So here's my set of rules. I like space games, and I like space TV shows and space books. So we'll think about a turn-based game with multiple players. And because we're talking about a big data technology, one thing that we'll keep in mind is, let's assume that this game can have hundreds or thousands of players. And so the amount of actual data that we're storing can be immense. For the purposes of our examples, we'll do only things that we can type, but we can imagine that anything that we see here should be trivially extendable to a case of actual big data, where you have lots of real-time data coming in from simultaneous clients and all of the considerations thereof. We'll do a space game, so it'll be like a space combat game. You'll have some civilizations, those are the players. Each civilization will have some units, those are some spaceships. What can spaceships do? They can pew, pew on each other, so they can fight each other. They have some score for how much they attack each other, how much they can defend themselves. Now, I don't believe in fast and light travel, so instead we have like systems, like solar systems, and the spaceships can move between them. So think about just squares on a board, they can move between them. And so the position of any unit is discrete. You're either orbiting one planet or orbiting another, but we don't care about what happens in transit. And just like a game like StarCraft, there's some capacity to mechanics. So there's some question of, do you win? You win by controlling the most territory. What considered to control the territory is that you have the most units in some particular space on the board. So you can think this is a fairly simple game. It's actually fairly simple to even games like Stratego. And the rule set, even though it's very small, actually ends up being fairly rich in terms of the modeling. We'll also assume that the way that the players interact with the game is that they'll issue orders. Our system will take in those orders. There'll be some game engine that just goes through those orders and pops them off and processes them. We won't write the game engine, and I'll tell you why in a moment. But we'll assume that they can just tell a ship individually, fire on this ship or maneuver. Those are the two typical things you can do, move and fire. And that's it. So it's a fairly simple set of mechanics, and we'll see how this leads to some data modeling. Now, the next thing that we want to think about are, what are the queries that we would encounter here? When we talk about SQL, oftentimes we ignore that it's really three separate languages that share a very clumsy common syntax. When people talk about SQL, they're talking about a query language, SQL. They talk about DML, a data modeling language, and they talk about DDL, a data modification language, and they talk about DDL, a data definition language. And even though they share the same syntax, or they share a similar type of syntax, and they have some similarities within them, they are in fact three fairly distinct things. We won't see very clearly how they're distinct, but one thing that you can imagine is, as Python programmers, one of the things that we're very used to and one of the conveniences that we rely upon is the availability of an incredibly dynamic system in which to write code. So if you think about it, one of the work mechanics that defined your use of a language like C or C++ is you write some code, you compile it, you go to lunch, you come back, and you run your tests. And in Python, you don't seem to have that very strict barrier between write some code, something happens as a compilation step, and then you run your test. It seems to be a little bit smoother. Similarly, in C and C++, it seems like everything's a little bit more static. You can't monkey patch things at runtime. You can't change the way the language works. Everything needs to have a very fixed layout in memory, and that layout exists every time, or is determined by the compiler and only exists at compile time, and there's no runtime representation of that. Bear in mind, as we look at SQL, and as you look at SQL more deeply in your careers, this is a very old technology from 1974, so that makes it 44 years old. That's ancient. Is there anyone here who's 44? If you're 44 years old, you're as old as SQL. That's really old. One of the things is, when you look at the history of programming languages, you'll see that certain things that we take for granted, like a very clear understanding of what's static and what's dynamic, or even things like modularity and functions and methods and objects, actually post-date things like SQL. So the modern programming environment, the things we say a programming language has to have to be a programming language, post-date SQL as a technology. This is a very old technology. This is why, in many cases, it seems incredibly clumsy to do things that are absolutely trivial. Okay, so let's actually get into the weeds of what we're going to do. So here's my little directory. I'll probably put this on GitHub at some point. Actually, no, I won't. Tweet at me if you want me to put this on GitHub. If you don't tweet at me, I won't. So if you really want to see the materials for this, you got to tweet at me. That's how you increase engagement. There's a couple of SQL files, and I'm going to do everything in SQL files. So I have 4 files here. There's helpers.sql, model.sql, data.sql, and queries.sql. And I've got a make file that helps things, makes things a little bit easy. And there's one little trick I'll do. Every time I save one of these files, you see it really quickly blinked a bunch of stuff on the bottom. Every time I save this thing, let me actually zoom down there. Every time I save this, it'll just rerun my tests in the background. So you'll see a couple of tests, and what I'll do is, oh, this one has a little bit of extra code in here. I'll just delete that, and delete that. And so I'll just remove the code that's here, because we'll write it ourselves. This is the first piece of code we'll write. Just remove that, and you can see there's an error because my files are incomplete. Now, of these files, the first one is helpers.sql. It's just some helper functions. It really isn't that interesting what's in here. Every project you start with has a bunch of stuff that you carry from project to project. They're just a couple of helper functions. Nothing too interesting. We will split this project into 3 parts. We'll do some data modeling. We'll actually insert some test data, and then we'll run some queries on this. So we'll actually see the wide gamut of everything that can be done in SQL. Now, let's actually get into this. So I told you at the very beginning that we have some players in our games, right? And we represent these as civilizations. So the 2 classical civilizations that we have in our game are the Earthers and the Spacers. Can anyone tell me something about Earthers? They're lazy, they're overpopulated, they live in caves of steel underground, they're an absolute mess. And we have the Spacers. They're erudite, they dress very nicely, they're very tall, but they're an existential crisis because they over-rely on robots, and they have a demographic crisis, and they'll never be able to survive a war with the Earthers. The Earthers tend to be more populated, and the Spacers tend to be more technologically adept. That has no bearing on the rest of this talk. I thought I would just share that with you. But we have some beginning part. So let's think about how we model this. Well, this is a really easy thing to model. Oh, one thing I want you to keep in mind, and I'll just show you before I get too deeper. Each one of these files is in, one of the things that's actually worth really understanding if you're doing SQL is the idea of data-first modeling. The idea that for many of you, when you have relational data, and you will always run into relational data, you usually will reach for an ORM. If you think about the actual work that you do, and the actual data source that you deal with. It's often the case that the core of the problem that you're trying to solve fits into a NumPy ND array or it fits into a pandas data frame. It's strictly columnar data or it's strictly matrix data, and the core, the meat of the problem, the thing that the deep learning person comes on stage to talk about is just a bunch of multiplications of those tensors or multiplications of those NumPy ND arrays or just some indexing and interpolation on that pandas data frame. But when you actually have to fit it into a real business problem, you start getting relational data. You start getting business entities that don't really have operational meaning within the system, that they're not part of some ND array. They have some complex set of rules governing what they can look like, and those rules are defined by the dynamics of the business environment in which they sit. So this is actually a fairly good fit for SQL. SQL succeeds at modeling business problems where you have relational data. When you start getting deeper into SQL, it's worthwhile to actually read through the documentation so that when you're writing SQL files, you can actually write kind of nice ones like this. Like you can see, there's a little bit of echoing when these run. As I'm running my tests, it has my follow me. This is called engagement. Always print on every slide, follow me at what, I learned that from somebody at PyData. You have nice logging here. I put everything inside transactions. And so there's a little bit of I'll start with a little bit of framework here just to make my life easier, and a common set of frameworks that one should start with when writing SQL. So as I said, we have some civilizations. So very simple to model it. We just create a table. Now, before we create a table, one thing that we need to know in Postgres is there's this idea of schemas. These are table spaces. They go by a lot of different names at different standards. When we are modeling this problem, we have to think fundamentally about what kind of queries we're going to apply to this data. So if we think about the business entities that exist in this system, there are entities that represent the game as defined, and there's business entities that represent the game as it's played. The business entities that represent the game as defined will fit into a schema called game. They're like, who are the players? Once the game starts, the players don't change. They'll be what the board looks like. Once the game starts, you can't add or remove units from the board. But between games, you might change what the board looks like because you might want to play bigger games or smaller games. What the units in that game are, the units definitions, the types of units, won't change within a game, but they may change between games. So there's some information that's not fully static, but only really changes between instances of a play of a game. And that's what's going to fit into the schema. And the first one is an idea of who the players are. So this is a very simple table to create. And we'll do a couple of things that we typically do on these. We'll give it a phony primary key so that a couple of queries will be easier later, with just an ID key, and just some name. Like that. And then when we run everything, we can see everything runs, and our little query down here for selecting the two players works. This is pretty easy. Now, the next thing we might want to do is we might want to define what the units in the game look like. And I told you that the units have some attack, they have some defense, they have some entities like that. So we could do the same thing. So again, it has some primary key. And now we get to see some things that are a little bit more interesting. It has maybe a name for the unit, so what kind of ship it is. It has some attack value. Maybe that's how much damage it does if it attacks. We can set defaults. When you think about your ORM style, all of this you could do with an ORM, but what gets really hard is to start adding simple constraints. And if you think about this, we have already, in our data-first approach, done something that is essentially very difficult to do in a guaranteed fashion with an ORM approach, which is to add constraints that ensure that the database is always in a consistent state. Now, one of the reasons that we'll practice this data-first modeling is that the actual clients that interact with this game may change over time, that the logic that we have in those clients might require a lot of repetition to enforce constraints, like we don't have ships that have a negative attack rating or a negative defense rating or cost a negative amount of money. And you can think within the logic of the client, within the logic of the game engine, there's a lot of places where you'd have to check these things. You might as well centralize those checks in the database. If you think about the database itself, it is a very complicated piece of software, and to use it as just a dumb store is an absolute waste. So that's kind of what it looks like for our units. Now, we can do things on this like create indices. We won't really do that for this talk. It'll take up too much of the very little time that we have left, but you can think we can create indices. Now, the other thing that we might want to do is we want to create the units on the board, and we'll call them solar systems. So create table if not exists, systems. And again, it looks very similar to before. In fact, they all have about the same fields. Now, one thing that I'm trying to do here is also encourage you, when you're writing your SQL, please don't write it like it's 1982, like that. You don't have to anymore. SQL is not really, the keywords are not case sensitive. Don't give names to the fields like, system name. There's proper namespacing, and you'll see me use this later on. There's proper namespacing and disambiguation of where things come from. Just as in Python, try and give things reasonable, human-readable, human-understandable names. Now, with that, the only last piece that I really need in order to complete my definition of what the game looks like is the wormholes that connect each system. And I don't need, and I can say this just goes from some system and it goes to some system. So here I can define, you can think I'm creating a more generalized board than like a square board. And one thing I can do is I can enforce that these are unique. So there's only one way to get from one place to another. Okay? So here I have a fairly simple exercise where I've modeled the state of the game entirely. And you can see, if not for two typos, one here and one here, everything just works. Now, with that, I can start actually creating elements in my data set to represent the state of the game. Now, just to save a little bit of time, I'll do a little bit of cut and paste from my notes. So because you don't really want to see me type that much. Oops. Oops. Okay, let's see if that works. Oh, I want to do this. I'll just do it by hand. Units, name, attack, defense, cost, values. We'll create 3 types of units, like little fighters, frigates, and maybe capital ships. And then we'll create 3 systems, and I'll try really hard to do ones that I can type correctly. Now, one thing that you can think that's interesting here is I've actually defined that these are static pieces of information, but they're not really. You could change these over the lifetime of the game. You could add units as the game evolves, but for the simplicity of this example, we won't. Now, if I wanted to, in my queries, I could do something like select star from civilizations, select star from systems. And you can see everything just works. Now, as I get into the dynamic data, the data that actually represents the game state, I start to see some things that are a little bit more complicated, where I need to do some more complicated constraints and modeling. I need to do more complicated queries. Let me show you 2 of those. The first of them is every player has some ships that they have, right? And as we go into this, we'll see there's some things that are very difficult to do automatically with an RM, but turn out to be very easy and very clean to just define if we take this approach of writing SQL, real SQL properly. So we create a table like that. And what we're going to do is we're going to say a ship belongs to some civilization. Civilization. A ship has some unit type. Units. A ship sits in some system. And a ship has some damage that it has accrued. Okay? And everything still works. Now, there's one thing that I want you to think about right here, something very interesting. All of you probably have some baseline familiarity with SQL. You know select, you know insert, you know update. If you think about those 3 verbs from the most naive perspective, one thing that you might think is, okay, an entity on a table represents an active entity. I insert it to create an active entity. I select to view. Select is a very interesting but very distinct verb. But when that entity no longer exists, like when the ship is destroyed, maybe I delete it from the table. When the ship moves, I probably update. I probably update what system it's in. When the ship takes damage, I update this. And if you try and take that same thought process and you apply it to some real-world business problems, you'll see that sometimes it breaks down. For example, going back to the typical example that people use when talking about SQL, the salary table. You have employees on a table. If an employee is in the table, it's an active employee. When you update the employee's salary column, that means they got a raise. When you delete an employee from that table, it means the employee's been fired. Well, here's a problem. You fire an employee. 3 months later, you need to do some tax accounting. You go back to your database, and you say, I removed that row. I can't do anything. Or you accidentally give an employee a raise, and you realize, I need to rewind you to the previous salary. What was that value? And one of the typical responses to something like this is people will do something like add a if valid, or they'll make these databases insert only. They'll say, really, if I wanted to make this a completely consistent model, I really shouldn't have the damage here. I should have another table that represents all the attacks that are done, and then I'll do some aggregate function on that. I'll do a map reduce on that, and I'll give me the damage, and then I'll fold that together. The problem is you'll end up taking this very rich vocabulary that SQL has of these core 3 modification verbs, update, insert, and delete, and you'll reduce it to just insert only. You'll have some insert only, append only store, and it will be consistent, but it'll be much, much less rich. Let me show you one of the key solutions and one of the key things missing to almost every initial data model whenever people are modeling relational data. And it's a concept called bitemporality. Here's the core idea. I want to know the history of my database every time there's a change. Every time a row changes, I want to store some information representing what that row looked like originally. I want to be able to use the core verbs of insert, delete, and update to represent exactly what they say they mean. Delete means this is no longer active. Update means this changed. Insert means this is a new entity. When I update and delete, I want to retain the history of what that table looked like before, so I can rewind to any point in time and say, what did this table look like as of this point in the game? Because as we start to model this deeper, one thing that you can think that's actually fairly interesting is if people are actually playing this game, and after they're done playing this game, we'll have captured a lot of information about how the players played, how they moved their units around, which somebody could then take and read in order to figure out strategies. This is useful data for analyzing strategies. You could pull this into a pandas data frame and try to do some kind of guessing around what strategies were employed by different players, but only if you had the historical view of all the table. The SQL 2003 standard, it's 2003 or 2006, added a concept of full temporality. Here's what it means. For records in a database, oftentimes they'll have some number of timestamps associated with them. If they are time series data, like for example, when you issue an order, the time when you issue that order is meaningful. If it's something like a ship, then there's no natural timestamp on that. For every one of those columns, we add one more timestamp, which is often called a system time or a knowledge time. The idea is we want to record in this table what does the row look like, what is the time that represents that row, like what was the time of the measurement we took, and what was the time which the system knew on that measurement. This tends to be a very complicated thing to do manually. And originally in databases, people would do this manually. They'd add something like an as of column, and they do a bunch of junk here, and they'd have, if you think about it for the employee example, what they do is they'd add a column called is current employee, and they toggle it from true to false when somebody leaves, so the database would just be insert only, and you'd just be adding rows. Very, very wasteful, because you end up having a really big table with mostly dead employees if you have high turnover. I want to show you something that actually is really nice about SQL and really nice about Postgres. There's a folder here in my repo called bitemporal, and in this folder, I have 2 files that I won't actually edit. One of them is a simple shell script that just goes through every single one of the tables that I have, and it'll identify tables that aren't history tables or aren't internal use tables, and it'll just run a simple Jinja template on some templated SQL. And the templated SQL just looks like this. A couple of alter tables and a little trigger. In Postgres, there is a user-provided plugin that you can find on GitHub that's on the Wikipedia page talking about full temporality, that adds full temporality to a Postgres database. It's just a plugin, and it's just a snippet of SQL that you run against every table. It's the exact same snippet of SQL that you run against every single table. So this snippet here I use for every single project. I don't even change it. In fact, I should probably add a pull request to the original project to just give it to them so that you could just run that plugin against every table. Let me show you what it does. I'll go into my make file, and I'll just turn on my little thing that runs my bitemporal. I'll show you what happens. Okay. So I'll run this, and I'll look at my tables now. Just make sure I did that right. Test bitemporal. Oh, I need to do it here as well. Okay. And if I go into my shell here, here are my solar systems. You can see it automatically inserted this as of table. What this as of table represents the system time. It represents the time which this row is active. In my active table, every system, or actually I'll do it on ships, which will change, right? Actually, let me insert some ships first, and I'll show you this example. So I'll do insert into ships, station, unit, system, and as I said, the spacers have very high technology, so they have a capital ship. Spacers. And we'll just stick it there. Okay, then we'll run our test, and then we'll look at the results in our shell. So you can see there's one row here. Now let's say this ship is destroyed. What I might do is I might do a delete from ships where ID equals 1. This is our naive approach. And when I look at the ships, it's gone. But when I want the history, this plugin, actually warehoused all the information, if I can type this right, warehoused all the information representing that. So every time a record is changed, I get that record stored automatically for me. I'll show you that again. Here's my ship. Let's update the system. Let's say it moved. Right? If I look at my history table, what I can see is I stored all the information about the history of this. And this uses a feature in SQL called table inheritance. What happens when I query from this table is I actually see the entire historical view of everything that happened. And that as of column is a date range for when that row was active. So here I have all the benefits of full temporality. I can always ask my database, give me the state of the game as of this point in time. And it can tell me exactly what the state of the game looked like at any point in time. But the schemas, the table definitions I have can actually use this naive approach for the verbs. So there we go with that. Now let me do the following. Let me go into my notes, and I'll add a couple more ships. And I'd really rather cut and paste this, so we'll add a bunch more ships in a bunch more places, and we'll look at the next part of this. Boy, those dirty spacers. Blowing up my cut and paste. Let's see if my cut and paste works. Ah, there we go. So we added a bunch more ships. Thank goodness for cut and paste. And let me just make sure I pasted that right. Oh. This is a fighter. What is it called? And this is a frigate. Oh. We gotta do one more thing, capital. We'll try this one more time and then figure which of these is wrong. Okay. Yeah. No, I'll wrap up. So the next part that I'm going to do, we'll get that to work in just one second. But the next part that I want to do is I want to show you how we can do the control. And the control is a fairly difficult thing to get right. And I just want to get this working. Sirius, Vega, and Rigel. Uh-oh. There's one more problem in here. Let's just remove these two, and we'll get this working. I want to show you the last part of this, which is how we actually figure out how to do a complex query here. So let's say that we want to figure out who controls what unit of space. That's a fairly complex query. What we might do is we might select star from the ships. And we might select it from the ships in the systems. So we can see every ship in every system. And we might do a join here. So we might select star from the ships, or from the systems, join the ships on the IDs being the same. So that's every ship in every system. And let me make this a little bit easier to read. So that's every system, and we'll see every ship in every system. Oops. So that's every ship in every system. Now, one of the things that we end up doing when we don't take a data first or a query first approach is we end up re-implementing a lot of very simple SQL query logic in our application layer. And so we end up doing lots of round-trip queries where a single concrete SQL statement can do it much more effectively. And I want to show you an example of that. And then once I show you an example of that, I'm going to switch over to my prepared version of this, and I'll show you one or two things that were a little bit harder. No, I'll skip the questions. Okay. So let me show you this. One of the things I want to do is I want to figure out who has the most ships in which area of space. And so what I'm going to do is I'm going to do a window function. I'm going to take this information, and I'm going to compute the rank over our partition of this information partitioned by the system name. And what I get when I do that and that's ordered by. And I have to do a group by at the end. There we go. So this is the ranking of how many. This is the ranking of how many civilizations have what ships in what places. In this case, you can see. Actually, let me switch over to the pre-prepared version. It's a little bit easier to see in that one. Whoops. There we go. And so you can see in this pre-prepared version, I have a bunch of ships in a bunch of places. And you can see in one case in this one system, there's two civilizations that have the same rank. Now I can make this a little bit easier to read by doing one more join. S dot. There. I can make this a little bit easier to read. And I'll do this as c.name. And you'll see that a query like this is actually much easier to do in a single form than you'd think. So there you can see we have some contention here, where in this particular system, two people have the same civilization, or the same thing. And this is what's called a window function. Essentially, when I'm doing this processing, oftentimes what we'll do is we'll pull in a bunch of data, we'll stick it into a pandas data frame, and we'll do window functions on that. We'll look at partitions of it. But it turns out that the SQL standard is much richer than that. It can do some of these window functions itself much more efficiently than you'd think. The way to actually resolve this, to figure out what I want to do, don't I have 2 minutes? Okay. So let me finish this example, and then I'll show you. So the end of this example looks like this. Which is that I end up creating a materialized view over this information with a window function that then allows me to identify these. Unfortunately, I ran out of time to show you the entire example, but you can see the general idea here is that it's a very rich language with a lot of very sophisticated ways to do things. Even for an example here with a very simple set of rules, you can start adding extra constraints. There were a couple of things I didn't have time to show you in the model itself, which was the idea that we can also do tree data. We can also do tree structured data where you tell one ship to do one thing and it cascades to everything else within the database itself. You can do sophisticated things like this, materialized views, wherein you kind of partition the information. You look for systems where everybody has the same number of units and you eliminate them. Very sophisticated queries that are otherwise impossible to do with an ORM. And from this approach, we end up having a data store that's itself consistent, enforces a lot of the business logic, can have raw queries against it, and leads to a very thin, very simple, and very easy to write application layer. Thank you.